In the early years of the 20th century, the scientific world found itself standing at the edge of an unexplored frontier. Classical physics had given humanity extraordinary predictive power over nature. Mechanics described motion, thermodynamics explained heat, and electromagnetism unified electricity with magnetism. Yet despite this elegant structure, something essential remained unexplained: the strange and stubborn behavior of atoms. These tiny building blocks of matter refused to obey the rules that govern planets, pendulums, or projectiles. Their spectra, their stability, and their emission of light all hinted at a hidden layer of physical reality that classical theories could not penetrate. It was into this enigmatic territory that Niels Bohr, a young Danish physicist with a sharp intuition and a bold willingness to challenge orthodoxy, would step. The idea he introduced quantized energy levels within atoms would do more than solve a puzzle. It would redefine the very language of physics, giving birth to an entirely new way of thinking about nature. To appreciate the magnitude of Bohr's insight, one must imagine the intellectual atmosphere before his breakthrough. Atoms were widely believed to exist, supported by the growing evidence from chemistry and kinetic theory, but their internal structure remained a mystery. Early models like J.J. Thomson's plum pudding concept pictured the atom as a sphere of positive charge with electrons scattered like raisins throughout. This was an attempt to explain electrical behavior, but it could not describe the subtle patterns of light emitted by gases when they were heated or electrified. Then, in 1911, Ernest Rutherford proposed a radically different picture. Based on his gold foil experiment, Rutherford concluded that atoms consist mostly of empty space, with a tiny, dense, positively charged nucleus at the center and electrons orbiting around it. This vision was a dramatic step forward, yet it created more problems than it solved. According to classical physics, an electron circling a nucleus should behave like an accelerating charge, losing energy by radiating electromagnetic waves. Within a fraction of a second, it should spiral into the nucleus, causing the atom to collapse. But real atoms are stable. They do not implode. Something crucial was missing. The spectral lines of hydrogen, analyzed through prisms and spectroscopes, provided another clue. Instead of emitting a continuous rainbow of light, hydrogen produced sharp, discrete lines at specific wavelengths. These precise fingerprints suggested that something about the atom's internal arrangement allowed only certain energies, not all possible ones. Scientists had hints that quantization played a role, primarily from Max Planck's work on blackbody radiation and Einstein's explanation of the photoelectric effect. Yet these earlier breakthroughs dealt with the quantization of light energy. No one had dared apply the same radical idea to the internal structure of the atom itself. The atom, after all, was considered a physical object, not a mysterious quantum system. Bridging the gap between the familiar world of matter and the emerging world of quantum required someone who could see beyond the boundaries of classical intuition. This is where Niels Bohr made his entrance. Bohr possessed an unusual blend of mathematical skill, philosophical depth, and physical imagination. He recognized that classical physics had reached a point where its principles could describe macroscopic phenomena with astonishing accuracy, but completely failed at the atomic scale. Instead of trying to patch the old theory, Bohr took the bold approach of discarding its core assumptions when necessary. He embraced the possibility that nature might behave differently at the smallest scales. While working in Manchester under Rutherford, Bohr became deeply intrigued by the instability of classical atomic models and the mysterious regularities of hydrogen spectral lines. These two puzzles, atomic stability and spectral precision, pointed toward a single hidden principle. Bohr's insight was to merge these clues with the quantum idea already hinted at by Planck and Einstein. In 1913, Bohr published his groundbreaking model of the hydrogen atom. He proposed that electrons do not orbit the nucleus in arbitrary paths, but instead occupy specific, quantized orbits. In these orbits, electrons do not radiate energy, completely defying the classical expectation. Energy is emitted or absorbed only when an electron jumps from one allowed orbit to another, with the energy difference corresponding to the frequency of the emitted light. This simple but radical idea explained hydrogen's spectral lines perfectly, matching the Balmer formula that had puzzled scientists for decades. Suddenly, What had once seemed an arbitrary mathematical pattern found its physical explanation. Bohr's model revealed that atoms were not miniature solar systems obeying Newton's laws, but quantum objects governed by discrete rules. The notion of quantized energy levels may appear straightforward today, but at the time it was almost unthinkable. To suggest that electrons could inhabit only certain allowed energies was to make a claim about the very structure of nature. It was not merely a mathematical trick, it was a statement about the way matter behaves at its core. In Bohr's view, electrons were not free to roam the continuum of energies predicted by classical mechanics. Instead, they were bound by a deeper, more fundamental law. Quantization was not an exception, it was the rule. This conceptual leap required abandoning centuries of deterministic thinking and embracing a universe where discontinuity and limitation were intrinsic features. Bohr's idea of quantized energy levels did more than rescue atomic theory. It introduced a new kind of reasoning. For generations, physicists had been trained to think in terms of smooth functions and continuous variables. The trajectories of planets, the flow of fluids, and the propagation of waves all followed this paradigm. Bohr's model shattered the continuity mindset by asserting that nature, at the atomic level, behaves in jumps rather than in flows. Electrons do not slide gradually from one energy to another, they leap. These leaps, or quantum jumps, represented a fundamentally different mental model of physical processes. Classical intuition no longer applied, and a new logic had to be developed. The quantized atom also provided a powerful framework that extended beyond hydrogen. Although Bohr's precise model would later be refined by quantum mechanics, its core idea that atomic behavior is quantized remains one of the foundational truths of modern physics. Every chemical element, every molecule, and every bond owes its existence to quantized energy levels. Why are atoms stable? Why do elements have characteristic spectra? Why do chemical reactions occur in predictable ways? The answer to all these questions begins with Bohr's revolutionary insight. Stability arises because electrons can reside only in discrete energy states, preventing collapse. Spectra arise because transitions occur only between specific levels. Chemistry works because electron levels determine how atoms interact and combine. In this sense, quantized energy levels do not merely describe atomic behavior, they create it. Yet the significance of Bohr's idea goes even deeper. By proposing quantized orbits, he implicitly introduced the concept that classical laws cannot describe reality at all scales. This was not just a new theory, it was a new worldview. It suggested that the universe operates with rules that change depending on scale. On the atomic level, quantization dominates. On the human level, continuity appears. Bohr's genius lay in seeing that the quantum world was not a reduction of classical physics but a replacement of it. The atom did not follow the old laws even approximately. It required a new set of principles altogether. These principles would eventually become formalized as quantum mechanics, but Bohr's energy levels were the philosophical and scientific doorway through which this new theory would emerge. The documentary of Bohr's contribution would be incomplete without addressing the intellectual courage required for such a proposal. Introducing quantized energy levels challenged not only existing theory, but also the deeply held beliefs of the scientific community. Many physicists were reluctant to abandon classical continuity. Some considered quantization an arbitrary assumption, a temporary patchwork solution. But Bohr insisted that quantization was not an add-on, it was a glimpse into the true nature of atomic structure. His conviction stemmed from the overwhelming explanatory power of the idea. When spectral lines and atomic stability fell into place with mathematical precision, it became impossible to dismiss quantization as a mere hypothesis. The impact of Bohr's insight rippled through the scientific world. His model sparked debates, inspired research, and laid the foundations for further advancements. Werner Heisenberg would later build matrix mechanics by focusing on observable quantity, drawing heavily on the logic Bohr introduced through quantized transition. Erwin Schrödinger's wave mechanics would reinterpret energy levels as standing waves around the nucleus. Even modern quantum field theory, with its emphasis on discrete excitation of fields, can trace its conceptual lineage back to Bohr's atom. In this sense, quantized energy levels were not just a discovery, They were a turning point in the history of human thought. Bohr's idea also carried profound philosophical implications. The notion that electrons occupy only specific energies and that transitions between them occur in jumps forced scientists to reconsider the nature of explanation itself. Classical physics offered clarity, predictability, and visualization. Bohr's quantum atom offered mystery, probability, and conceptual leaps. The world was no longer a machine evolving smoothly in time, but a dynamic canvas where events unfolded in discrete steps. This conceptual transformation, initiated by the quantized atom, influenced not just physics, but philosophy, logic, and the study of knowledge. Bohr's introduction of quantized energy levels did not merely answer a scientific question, it introduced a new intellectual landscape in which traditional assumptions could no longer survive. Before his work, scientists believed that the microscopic world should mirror the macroscopic one. If planets could move freely in continuous orbits, then surely electrons must do the same. Bohr shattered this assumption and demonstrated that the universe has layers of rules. What appears continuous to us may be fundamentally discrete at its core. His work illuminated the idea that human intuition, shaped by everyday experiences, is not a reliable guide to understanding the natural world at its smallest scales. This realization marked a monumental shift in scientific reasoning. As researchers explored Bohr's model further, it became clear that the quantized atom solved not one problem but many. The previously mysterious hydrogen spectral series suddenly fit into place with astonishing accuracy. The mathematical relationship between wavelengths, discovered by Johann Balmer decades earlier, was now grounded in physical principles. Bohr's formula for the energy levels of hydrogen matched experimental data so precisely that it became one of the strongest confirmations of quantum ideas in early atomic theory. Even skeptics had to reckon with the undeniable success of a model built on quantization. This concrete triumph forced the scientific community to confront an uncomfortable truth. Nature did not care whether quantization was philosophically pleasing. It simply behaved that way. The introduction of quantized energy levels also revealed the astonishing stability of atoms. Classical physics predicted that electrons, constantly accelerating in orbit, should radiate energy and dive into the nucleus. But Bohr showed that when electrons occupy specific, quantized orbits, they experience no energy loss. These orbits were not arbitrary, they were the architecture of the atom. Without quantization, matter would collapse instantly. Every atom in the universe owes its stability to this principle. The persistence of matter, the structure of the periodic table, and the existence of the physical world all depend on electrons being restricted to discrete energy states. Bohr had uncovered not just a rule but the foundation upon which all of chemistry and material existence rests. This shift in understanding did something else profound. It revealed that energy itself is not a smooth continuum but comes in packets or quanta. While Planck had proposed quantized energy for light, Bohr extended that idea to matter. By doing so, he presented the first unified view of the quantum world. Light and matter, previously considered entirely different, were now governed by the same underlying principle. The atom became the bridge between these realms, and Bohr's energy levels served as the blueprint for this connection. This unified perspective opened the door to the development of quantum mechanics, which would soon evolve into one of the most successful scientific theories ever created. As more physicists engaged with Bohr's model, it became clear that it could not be the final answer. Bohr himself knew that his model was incomplete. It used classical orbits and quantum rules inconsistently, a hybrid construction that worked remarkably well for hydrogen but struggled with more complex atoms. Yet, rather than being a weakness, this incompleteness became an inspiration. Bohr's energy levels acted as guideposts that pointed toward a deeper, more consistent theory. Heisenberg, Schrödinger, and Dirac would later follow these guideposts to build quantum mechanics, but the conceptual skeleton they used had been supplied by Bohr. His quantized atom demonstrated where classical physics broke down and where new principles were required. The documentary-style narrative of Bohr's contribution must highlight the human element behind this intellectual revolution. Bohr was not a scientist who generated theories in isolation. He was a mentor, collaborator, and philosophical guide. He believed deeply in open dialogue and the exchange of ideas. At his institute in Copenhagen, he cultivated an environment where young physicists could challenge assumptions and debate freely. Many of the pioneers of quantum mechanics passed through Copenhagen, absorbing Bohr's perspective on quantization and his insistence that new physical truths sometimes demand abandoning old ways of thinking. The quantized atom was not simply a scientific proposal, it was the cornerstone of a new scientific culture. One of the most striking aspects of Bohr's quantized atom is how quickly it forced scientists to rethink the nature of measurement. In classical physics, measurement was a passive activity. One could observe a system without disturbing it. But Bohr's model, with its sudden quantum jumps between energy levels, suggested that the act of observing might influence the system. Later developments in quantum mechanics would formalize this notion, but the philosophical groundwork was laid by Bohr's realization that atomic energy changes occur in discrete steps triggered by interaction. The atom was no longer a silent, predictable machine. It was a dynamic, reactive system shaped by interactions and observation. This philosophical shift echoed throughout 20th century science and continues to influence debates about the nature of reality. The quantized energy level model also had ripple effects beyond physics. By introducing discontinuity into the heart of matter, Bohr challenged long-standing assumptions in philosophy, mathematics, and even classical logic. Many thinkers were troubled by the notion that an electron could jump between levels without occupying the space in between. Such jumps seemed to violate the common-sense notion of continuity. Yet experiments validated these transitions repeatedly. The universe did not behave like the smooth, predictable world imagined by classical philosophers. Instead, it operated through discrete states, probabilities, and sudden changes. The atom, once thought to be a tiny clockwork mechanism, turned out to be a quantum system with rules unlike anything seen in human experience. As scientists probed deeper into Bohr's model, they realized that the concept of quantized energy levels had implications far beyond atomic structure. In molecular chemistry, the arrangement of electrons in quantized orbitals determined how atoms bond, how molecules vibrate, and how chemical reactions proceed. The shapes of molecules, the colors of substances, and the behavior of materials all stem from quantized levels. From the simplest hydrogen atom to the most complex organic molecules in living organisms, the principle of discrete energy states governs the interactions that sustain life. Without Bohr's insight, the logical structure of modern chemistry would be incomprehensible. The impact extends to technology as well. Lasers function because electrons transition between quantized energy levels in a controlled manner. Semiconductors, which form the backbone of modern electronics, rely on energy bands created from quantized atomic states. Even quantum computing, which manipulates information using quantum states, traces its conceptual origins to Bohr's energy levels. In this sense, Bohr did not merely describe atoms, he provided the foundation for entire industries. The digital world of the 21st century owes much of its existence to the discrete nature of atomic energy that Bohr revealed over a century ago. It is also important to recognize the elegance of Bohr's insight. At a time when atomic theory was full of contradictions, Bohr introduced a model that was surprisingly simple yet profoundly accurate. His energy level formula predicted the Rydberg constant with extraordinary precision. This was not a coincidence. It was evidence that Bohr had tapped into a deep truth about nature. His willingness to ignore classical intuition and embrace quantization allowed him to see patterns that others had overlooked. This capacity to accept the counterintuitive is one of the hallmarks of quantum thinking, and one of the reasons Bohr remains such a towering figure in the history of science. The resistance Bohr faced also reveals the magnitude of his achievement. Many prominent scientists initially dismissed his ideas as ad hoc or philosophically dubious. Some accused him of abandoning scientific rigor in favor of assumption, but as experimental evidence accumulated in support of his prediction, even critics had to acknowledge the power of the quantized model. Bohr's colleagues recognized that he had opened a door to a new world, a world in which classical physics could not survive. The debate sparked by Bohr's model helped shape the development of quantum mechanics, forcing researchers to confront contradictions and refine their theories. In this sense, the controversy surrounding Bohr's quantized atom played a crucial role in advancing physics as a whole. Bohr's work also paved the way for a new kind of scientific humility. Classical physics had promised a fully deterministic universe where every event could be predicted with perfect accuracy if one knew the initial conditions. Bohr's energy levels, however, hinted that certainty might not be a fundamental feature of nature. If electrons could exist only in certain states and transition unpredictably between them, then the universe might be inherently probabilistic. This idea would later be formalized in Heisenberg's uncertainty principle and the probabilistic interpretation of the wave function, both of which were shaped by Bohr's philosophical guidance. Thus, the quantized atom was not only a scientific breakthrough, it was a conceptual turning point that forced humanity to rethink the nature of knowledge. As the 20th century progressed, the quantized model became a launching pad for deeper and more comprehensive theories. Schrödinger's wave equation provided a mathematical description of allowed energy states, replacing the idea of rigid orbits with probability distribution. Dirac extended the theory to incorporate relativity, predicting antimatter and revealing new symmetries. Despite these advancements, the essential structure, first proposed by Bohr, remained intact. Energy levels were discrete, transitions occurred in jumps, and atomic behavior was fundamentally quantized. These principles are now cornerstones of physics, enduring through generations of scientific progress. Bohr's insight was not a temporary solution, it was a foundational truth. What makes Bohr's contribution even more remarkable is the clarity with which he recognized the philosophical implications of quantization. He did not treat quantum rules as mechanical instructions but as clues to a deeper reality. He saw that the quantum world required a new conceptual framework, one that embraced complementarity, duality, and limits of knowledge. The quantized atom was the first step toward this new framework. It was the spark that illuminated the strange landscape of quantum physics, guiding scientists through its paradoxes and complexities. Bohr's ability to see beyond equations and into the philosophical heart of physics set him apart from his contemporaries. In the grand narrative of scientific discovery, Bohr's introduction of quantized energy levels stands as a defining moment. It marked the birth of quantum thinking, a shift from classical certainty to quantum possibility. It opened the door to a universe that behaves differently than the one we experience daily, where particles exist in probability clouds, where measurement affects reality, and where energy comes in discrete packets rather than continuous flows. Bohr's insight transformed not only the atom, but the entire scientific worldview. Every modern physicist, whether consciously or not, works within the conceptual universe that Bohr created. The story of quantized energy levels is therefore not just a tale of scientific progress, it is a story about the evolution of human thought. It shows how a single idea, introduced at the right moment by a mind willing to challenge conventions, can reshape our understanding of reality. Bohr's willingness to embrace the unfamiliar and the counterintuitive allowed him to see truths hidden from others. His model revealed a world that defies classical logic, yet operates with astonishing precision. In doing so, he gave scientists a new way to think, a new way to question, and a new way to explore the mysteries of the universe. The significance of this achievement becomes clearer when one considers the sheer scale of its impact. Every electron in every atom follows the quantized structure Bohr described. Every chemical bond, every spectrum of light, every technological device built on semiconductors, lasers, or quantum principles all trace their origin to the moment when Bohr declared that electrons occupy discrete energy levels. The physical world as we know it, from the behavior of gases to the workings of biological systems, is shaped by this principle. Without quantization, matter would behave chaotically, chemistry would not exist in its recognizable form, and life itself would be impossible. It is because of these profound implications that Bohr's introduction of quantized energy levels is considered one of the greatest intellectual breakthroughs in history. It was the moment when humanity began to grasp the true nature of the microscopic world. It marked the beginning of quantum thinking, framework that still guides physicists today as they explore quantum information, quantum fields, and the depths of reality. Bohr did more than solve a problem. He changed the trajectory of science. His energy levels were not the end of the story, but the beginning of a revolution. The scientific world of the early 20th century was built on a remarkable confidence in classical physics. For more than 200 years, Newtonian mechanics had provided an elegant and seemingly complete description of motion. Maxwell's equations unified electricity and magnetism, offering a majestic picture of electromagnetic waves, including light. Thermodynamics described heat and energy with precision. With so much success behind them, many physicists felt that nature had surrendered most of her mysteries. Only a few clouds, as Lord Kelvin famously remarked, seemed to trouble the horizon. Yet hiding inside those clouds was a revolution, waiting to unfold, a revolution that would dismantle classical certainty and replace it with the strange, counterintuitive logic of the quantum world. The spark of this revolution was Niels Bohr's model of the hydrogen atom, an idea so bold and unconventional that it divided the scientific community, challenged long-held assumptions, and transformed the very foundations of physics. To understand why Bohr's hydrogen model broke classical physics, one must first appreciate the depth of the classical worldview. According to classical theory, objects move continuously through space, forces act smoothly, and energies change in measurable, predictable ways. Even in the microscopic realm, it was assumed that atoms followed the same principles as planets and pendulums. If one understood the forces acting on an electron inside an atom, one could, at least in principle, calculate its path, energy, and motion. The atomic world was expected to be merely a smaller version of the macroscopic world. That belief, deeply rooted in centuries of scientific achievement, guided every major physicist of the 19th century. But classical reasoning began to fail whenever science turned its focus to hydrogen, the simplest and most abundant element in the universe. Hydrogen emitted light in very precise wavelengths, forming a pattern of spectral lines that defied classical explanation. Spectroscopy revealed that hydrogen did not emit a continuous rainbow, but instead produced sharp lines at fixed positions. This implied that the atom released energy in specific amounts, not in arbitrary values. For classical physics, which relied on continuity, this was nothing short of a crisis. Why would an atom behave in such a quantized manner? What mechanism inside the atom restricted energy emission to exact intervals? No theory based on classical laws could provide an answer. Then there was the puzzle of atomic stability. Rutherford's nuclear model showed that atoms consisted of a tiny central nucleus surrounded by orbiting electrons. But according to classical electrodynamics, an accelerating charge, like an orbiting electron, should continuously emit radiation, losing energy and spiraling inward until it crashed into the nucleus. This catastrophic collapse should occur in a fraction of a second, meaning atoms should not exist at all. Yet the world was clearly made of stable atoms. Classical physics offered no escape from this contradiction, no principle that could halt the continuous loss of energy predicted by its own equations. The atom, the very building block of matter, stood in open defiance of classical laws. Into this crisis stepped Niels Bohr, a young Danish physicist driven not by comfort with established ideas but by a restless desire to uncover the truth hidden beneath nature's surface. Bohr was deeply influenced by the quantum idea introduced by Planck and Einstein particularly, the notion that energy under certain conditions comes in discrete packets. But Bohr saw further than most. He recognized that quantization was not merely a mathematical device for solving radiation problems. It was a fundamental principle of nature. It was not just light that was quantized. The structure of the atom itself demanded quantization. The classical picture of electrons smoothly gliding through continuous orbits had to be abandoned. Bohr proposed a radical new idea. Electrons occupy only certain allowed orbits around the nucleus, and each orbit corresponds to a fixed energy level. While in one of these stable orbits, an electron emits no radiation whatsoever, even though classical physics insists it should. Energy changes occur only when the electron leaps from one orbit to another, releasing or absorbing a precise amount of energy equal to the difference between the two levels. These quantum jumps, instantaneous transitions without classical motion in between, were unlike anything known in physics. Nothing in everyday human experience prepared scientists for this idea. It was irrational from the perspective of classical mechanics, yet it predicted hydrogen's spectral lines with astonishing accuracy. This accuracy was not accidental. It was the first great blow to classical physics. Where classical theories had failed spectacularly, Bohr's quantum-based model succeeded with precise numerical predictions. It offered a clear explanation for hydrogen's emission spectrum, mathematically reproducing the Balmer series formula that had been known empirically but lacked theoretical justification. Bohr's bold step showed that classical reasoning could not be applied inside the atom. A new kind of reasoning, quantum reasoning, was required. Bohr's model broke classical physics, not through philosophical argument, but through undeniable empirical success. His formula for the energy levels of hydrogen matched experimental results perfectly. This match forced scientists to confront a truth they had long resisted: nature, at the atomic level, does not follow the continuous laws of classical mechanics. Instead, it operates through discrete states and quantized transitions. The classical idea that motion can be tracked smoothly and continuously broke down completely. Bohr had revealed a universe built not on continuity but on steps, jumps, and discrete structures. This shift was more than scientific. It was psychological. Classical physics had created an illusion of certainty, a belief that the universe could be known entirely through reason and measurement. But Bohr's model exposed fundamental limits. It hinted that the atomic world could not be visualized in classical terms, that the comfortable analogies used to understand everyday phenomena would collapse inside the atom. When electrons leap between energy levels without existing in intermediate states, classical intuition fails. Bohr's model forced physicists to rethink what it means to know something in science. Could one describe the path of an electron? Could one speak of its motion in the classical sense? Bohr's answer was a decisive no. By proposing that electrons do not follow classical orbits, Bohr opened the door to a new way of thinking in which the laws of nature are deeply probabilistic, contextual, and fundamentally different from anything experienced in the macroscopic world. Bohr argued that the atomic realm required unique principles, not analogies borrowed from the human scale. This was the birth of quantum reasoning, the intellectual shift away from deterministic trajectory and toward discrete states, dualities, and measurement-dependent realities. Bohr's ideas were shocking because they demanded that scientists accept paradox as a core part of nature. Electrons could behave like particles in one experiment and like waves in another. They could occupy one energy level or another, but nothing in between. They could be stable despite violating classical mechanics. These contradictions were not signs of incomplete understanding. According to Bohr, they were expressions of the quantum world's true nature. This philosophical shift marked a profound break with classical thinking, which had long demanded consistency, continuity, and visualization. Quantum reasoning was not merely a new set of rules, it was a new way of conceptualizing reality itself. Bohr's model also transformed the scientific method. Classical physics emphasized prediction through deterministic equations, but Bohr showed that certain information about atomic systems is inherently limited. His model suggested that not all properties can be simultaneously known or defined, a viewpoint that would later be formalized in Heisenberg's uncertainty principle. Even before the uncertainty principle was formally articulated, Bohr's hydrogen model carried its spirit. By focusing on energy levels rather than trajectories, Bohr implicitly accepted that electrons could not be described using classical paths. This acceptance helped pave the way for the probabilistic interpretation of quantum mechanics. The documentary perspective must highlight the shock, confusion, and debate that followed Bohr's publication. Many scientists dismissed the model as absurd or unscientific because it violated classical laws. Some argued that Bohr inserted quantization artificially without justification, but as experimental evidence accumulated, Bohr's predictions proved impossible to ignore. The model was not a convenient mathematical trick. It was a genuine window into the atomic world. Through Bohr's work, physicists realized that classical reasoning was not merely incomplete, it was fundamentally incompatible with atomic behavior. By breaking classical physics, Bohr did not destroy scientific understanding, he expanded it. His model revealed that the universe is layered, with different rules applying at different scales. At the atomic level, electrons inhabit discrete energy states. At the human scale, energies appear continuous. This discovery demonstrated that classical physics is a limiting case of quantum physics, not a universal truth. The macroscopic world follows classical laws only because quantum effects average out on a large scale. Bohr's hydrogen model was the first opening in the wall separating the classical domain from the quantum one, and once that opening appeared, a flood of new ideas poured through. Bohr's model not only redefined physics, it redefined possibility. By showing that atoms follow rules unlike anything encountered in everyday life, he encouraged physicists to explore deeper, more abstract theories. The hydrogen model inspired Heisenberg to develop matrix mechanics, Schrödinger to create wave mechanics, and Dirac to unify quantum theory with relativity. All these developments stemmed from the insight that classical laws fail at the atomic scale, and that new forms of reasoning are required. Without Bohr's model, the conceptual leap to full quantum mechanics might have taken far longer. Thus, the documentary account of Bohr's hydrogen model is not merely the story of a new theory, it is the narrative of a scientific revolution. A young physicist challenged the most cherished assumptions of classical physics and replaced them with principles that opened an entirely new universe of understanding. He broke the continuity of classical motion, introduced discrete energy levels, explained atomic stability, and illuminated the spectral fingerprints of hydrogen. Most importantly, he forced humanity to adopt quantum reasoning, a mode of thought that accepts discontinuity, duality, and uncertainty as fundamental aspects of reality. The deeper the scientific world ventured into the structure of the atom, the more it realized that the classical trail Bohr had disrupted could never again be recovered. His work did not only expose the cracks in the old worldview, it illuminated an entirely new terrain where intuition, experience, and even imagination had to be reshaped. In the years after his model was introduced, physics entered a period of breathtaking transformation. What began as a simple attempt to explain spectral lines evolved into a revolution that reshaped how scientists think about possibility, causality, and reality itself. The most remarkable thing was that Bohr did not merely inspire this revolution. He actively guided, corrected, mentored, and philosophically framed it. This is why his role is different from other giants of that era. He was not just a contributor. He was the thinker who helped everyone else understand what their discoveries truly meant. As more experimental data poured in, discrepancies in classical theory became impossible to ignore. Electrons did not behave like little planets, nor did energy follow smooth, continuous patterns. Even light, which had already challenged physicists through the photoelectric effect, now demanded a new conceptual space. In this restless scientific climate, Bohr's insistence on combining intuition with disciplined reasoning began to stand out. He understood that scientists needed permission to rethink the fundamentals without fear of contradiction. Bohr became that permission. His philosophy was not an abstract accessory to physics, it was the guiding map that allowed the field to evolve without collapsing into confusion. Within the walls of the Copenhagen Institute, a unique and radical culture took shape. Unlike many scientific centers that valued hierarchy and rigid protocol, Bohr's institute thrived on informal discussion, late-night debates, laughter, chalk dust arguments, and an openness that shattered academic barriers. Young physicists from all around the world came not simply to study equations but to learn how to think differently. They entered a world where the bizarre became normal and where uncertainty was not a flaw in understanding but a doorway to deeper truth. Every scientist who visited left with the same impression. Bohr had created a world where quantum thinking was not just taught but lived. This environment became the birthplace of some of the most groundbreaking concepts in all of physics. Werner Heisenberg's formulation of matrix mechanics was not the product of solitary genius. In isolation, it grew from prolonged discussions, arguments, and guidance in Copenhagen. When Heisenberg struggled to make sense of his own ideas, the place he turned was Bohr's office. There, he found not only critique but clarity. Bohr had a remarkable ability to see the direction of a new idea, even when its creator was unsure of it. He would ask questions that seemed simple but carried immense depth, questions that forced young scientists to articulate their thoughts with precision. Through these exchanges, Heisenberg began to refine the idea that would ultimately become the uncertainty principle. The principle itself is often discussed as if it suddenly appeared in the mind of a single physicist, but that is only half the truth. The philosophical foundation, the willingness to accept that nature resists classical determinism, was something Bohr had already planted through his doctrine of complementarity. This doctrine, though subtle, shaped the entire psychological landscape of quantum physics. It suggested, gently but firmly, that the world at microscopic scales could not be described by a single viewpoint. Instead, reality required multiple, seemingly contradictory descriptions that each revealed part of the truth. Heisenberg's breakthrough was thus not a departure from Bohr's vision but a flowering of it. This influence extended to many others. Young Wolfgang Pauli found in Bohr a mentor who could cut through his intellectual storms. Paul Dirac, quiet and reserved, found a space where his abstract, mathematical mind could express itself without fear of misunderstanding. Even Einstein, who disagreed with Bohr on fundamental interpretations, acknowledged that Bohr possessed a way of thinking about physics that was unmatched. Their debates were legendary, often stretching late into the night, producing the very argument that would shape the philosophical foundation of quantum mechanics. And though they disagreed, Einstein respected Bohr as the one mind capable of meeting him on the highest ground of theory and logic. As these intellectual exchanges unfolded, experiments began to catch up with theory. Each new piece of evidence, diffraction of electrons, the Compton effect, the double-slit results, reinforced the idea that Bohr's approach to atomic structure was part of a larger system of truth. The quantum world was not merely odd, it was fundamentally different. Bohr's insistence on seeing the atom as a system governed by discrete jumps, quantized orbits, and unpredictable transitions helped scientists accept experimental outcomes that defied classical explanation. When other physicists grew frustrated with contradictions, Bohr saw patterns. When they felt confused by paradoxes, Bohr saw opportunities for deeper understanding. He transformed scientific discomfort into intellectual fuel. The development of quantum mechanics did not proceed smoothly. It was riddled with doubt, resistance, and intellectual tension. Many great physicists feared that abandoning classical causality meant abandoning reason itself. They worried that science would lose its ability to explain the world. But it was Bohr, more than anyone else, who reassured them that reason was not being destroyed, it was expanding. His voice carried extraordinary weight because he spoke not as a dreamer, but as a scientist who had already demonstrated that radical ideas could lead to precise predictions. The hydrogen spectrum had validated his courage. Now his philosophical clarity would validate the entirety of quantum mechanics. Throughout the late 1920s and 1930s, Bohr's influence became so strong that major breakthroughs across Europe bore traces of his intellectual fingerprint. Even when he was not directly involved in the calculations, his thinking shaped the questions that physicists asked and the kinds of answers they accepted. The shift from classical to quantum thinking was not just mathematical. It was psychological and conceptual. Scientists had to let go of deeply embedded assumptions shaped by centuries of deterministic thought. Bohr provided the intellectual bridge that allowed this transition to occur without collapsing the logical framework of science. In a world shaken by war, shifting political landscapes, and rapid technological advancement, Bohr remained a stable pillar of scientific integrity. During World War II, as physicists across the globe were drawn into geopolitical struggles, Bohr's insistence on openness, exchange, and shared knowledge stood in stark contrast to the secrecy and fear spreading across Europe. Even as he contributed to important wartime efforts, he continued to champion the idea that scientific truth belonged to all humanity. His laboratory had always been a haven for international cooperation. Now he tried to preserve that spirit in a fractured world. After the war, Bohr continued to refine the philosophical implications of quantum mechanics. He understood that the true importance of the quantum revolution was not limited to atomic theory or mathematical models. It was part of a broader shift in human understanding. The universe was no longer a machine governed by simple, predictable rules. It was a dynamic, intricate system in which knowledge itself had limits. These limits were not weaknesses but fundamental characteristics of nature. Bohr believed that accepting these limits would lead to a more realistic, humble, and accurate worldview. This belief became a cornerstone of modern scientific thought. Young physicists of the next generation continued to seek Bohr's guidance. The Copenhagen Institute remained a center of intellectual gravity even as new fields such as nuclear physics and particle physics emerged. Bohr did not cling to his own ideas. He adapted, learned, and encouraged exploration. What made him a true figure in physics was not only his role in creating quantum theory but his ability to nurture and refine the thinking patterns of others. He was not a solitary genius tower, he was a catalyst who transformed the potential of countless minds. Even decades later, the language of quantum mechanics still echoes with Bohr's influence. Terms like complementarity, wave-particle duality, and quantum jumps all trace their conceptual DNA back to his thinking. Modern quantum technologies, from lasers to semiconductors, quantum computers to MRI machines, operate on principles that emerge directly from the intellectual world Bohr helped construct. Yet, despite the enormous impact of these technologies, Bohr's deepest legacy lies not in devices or discoveries, but in the transformation of scientific reasoning itself. The shift he initiated continues to shape how scientists approach complex systems. In fields as diverse as biology, information theory, and cosmology, the acceptance that systems can behave in multiple complementary ways has become essential. Bohr's influence extends far beyond physics. It reaches into philosophy, cognitive science, and the foundations of logic. He changed not only how we see matter, but how we understand knowledge. As the documentary camera metaphorically pans across the last century of scientific progress, it becomes clear that the story of quantum mechanics is not a chain of isolated discoveries, but a tapestry shaped by a guiding intellect. Bohr's philosophy, mentorship, humility, and vision turned a collection of strange experimental results into a coherent scientific revolution. He made room for uncertainty, paradox, and complexity at the heart of scientific reasoning. And by doing so, he liberated science from the narrow assumptions of classical thought. Bohr's true achievement lies in showing humanity that understanding the universe requires embracing its deepest mysteries. He taught that clarity does not always come from reducing the world to simple rules, but from expanding our capacity to accept new kinds of truth. The scientists who built quantum mechanics each contributed a piece, but it was Bohr who taught them how to connect those pieces into a new reality. This is why, when the story of quantum thinking is told, his presence looms larger than anyone else's, not as a conqueror of nature, but as a guide into its most profound depths. Through his vision, quantum thinking became not a mathematical framework, but a new form of reasoning. It allowed humanity to see the universe with new eyes, to question assumptions that once felt unshakable, and to understand that truth can have multiple faces. This revolution in thought is Bohr's greatest gift, and it continues to shape the frontier of science even today. In the realm of classical physics, the act of observation was considered passive, almost invisible. A scientist could measure the position of a pendulum, the velocity of a projectile, or the intensity of light, confident that the act of measurement would not disturb the system. The universe was assumed to operate independently of those who observed it. Reality existed in its entirety, waiting to be discovered, and the role of science was to uncover this pre-existing truth. This framework, which had guided centuries of physics, was suddenly confronted with a profound challenge by Niels Bohr's revolutionary ideas. Bohr's work on the atom, particularly his insights regarding measurement, demonstrated that at the quantum level, observation is not passive. Instead, it becomes a participant in the unfolding of physical phenomena. This realization marked a radical departure from classical assumptions and laid the foundation for a complete new understanding of nature, one in which the observer and the observed are inseparably linked. The origins of this insight can be traced back to Bohr's study of atomic structure and the behavior of electrons. Classical mechanics predicted that electrons should move continuously in orbits around the nucleus with energies that could be precisely defined at every point in time. Radiation emitted from these electrons was expected to follow the smooth and predictable laws of electromagnetic theory. Yet, experimental evidence consistently contradicted this assumption. Spectral lines of hydrogen and other elements appeared as discrete quantities rather than continuous emission. The universe at its smallest scale did not behave like the smooth, predictable machine that classical theory envisioned. Something about the act of interaction, whether it was emission, absorption, or observation, changed the system itself. Bohr recognized that these interactions were not incidental but central to understanding quantum behavior. In classical physics, measurement was considered an external process. Instruments could record values without influencing outcomes. A thermometer would register the temperature of water without affecting the molecular motion. A scale would measure mass without altering the object being weighed. Such assumptions underpinned centuries of empirical work, reinforcing a worldview in which knowledge was independent of the observer. Bohr's investigation into quantum phenomena shattered this notion. He realized that at the atomic and subatomic scale, measuring a system invariably changes it. For instance, to determine the energy of an electron or the frequency of emitted light, one must interact with it in some way, typically by exchanging photons or applying electromagnetic fields. These interactions are not merely passive observations. They actively influence the state of the system. The act of measurement and the behavior of the system are intertwined. This principle of observer influence was deeply tied to the concept of quantization. Electrons inhabit discrete energy levels, and transitions between these levels occur in sudden jumps. Unlike a ball rolling down a slope, which can exist at any height along its path, electrons do not exist in intermediate states between quantized orbits. When an experimenter attempts to measure an electron's position or energy, the very act of probing it affects which orbit it occupies. Bohr's recognition of this interplay represented a dramatic departure from classical determinism. Measurement was no longer a neutral process. It became an intrinsic part of the phenomenon being observed. The boundaries between subject and object, observer and observed, began to blur. Bohr's emphasis on the observer's role was more than a technical insight. It was a philosophical revolution. It challenged the deeply held assumption that physical reality exists independently of human intervention. In the quantum realm, knowledge of a system is inseparable from the methods used to acquire it. This idea, which would later be formalized in Heisenberg's uncertainty principle, forced scientists to reconsider what it means to know something. Prior to Bohr, accuracy and precision were achieved by minimizing interference, assuming that instruments could approach perfect neutrality. Bohr showed that no such neutrality exists at the atomic scale. To measure is to participate. To observe is to interact. Reality itself, in this sense, is conditional upon the act of observation. Bohr developed the principle of complementarity to address these paradoxes. He argued that quantum entities, such as electrons and photons, could exhibit mutually exclusive properties depending on the measurement context. A single experiment could reveal particle-like behavior, while another could reveal wave-like behavior. It is not that the system itself changes arbitrarily. Rather, the observed property is contingent upon the experimental setup. The observer, by choosing which measurement to perform, determines which aspect of the system becomes manifest. This principle encapsulated Bohr's revolutionary understanding. Observation and physical outcome are not separable. The reality encountered in the laboratory depends fundamentally on the interaction between experimenter and system. Bohr's insight emerged from rigorous attention to both theoretical reasoning and experimental results. Spectroscopy, the study of light emitted or absorbed by atoms, provided crucial evidence. When electrons transition between quantized energy levels, they emit photons of specific frequencies. But these photons are not emitted continuously or gradually. They appear in discrete quanta. Detecting these photons requires instruments that interact with them, influencing the electron transitions in subtle ways. Bohr recognized that the observed spectral lines were not merely passive traces of atomic activity. They were manifestations of an interactive process involving both atom and observer. In this way, the data itself provided direct evidence of the inseparability of measurement and outcome. The implications of Bohr's perspective extended far beyond atomic physics. By emphasizing the observer's influence, he introduced a conceptual framework in which certainty and determinism must be redefined. At the quantum level, it is impossible to know all properties of a system simultaneously with infinite precision. Measurement imposes fundamental limits, not because of technological shortcomings, but because nature itself is structured in this way. This principle challenged the centuries-old notion that science could achieve complete, objective knowledge. Bohr's insight demanded a new methodology, one that acknowledges the constraint imposed by the act of observation and the context of measurement. Bohr's recognition of the observer's role also influenced the interpretation of quantum experiments. Consider the famous double-slit experiment. where electrons passing through a pair of slits can display either wave-like interference or particle-like behavior depending on the measurement setup. Bohr would argue that this phenomenon is not a deficiency in experimental design or a limitation of technology. It is a fundamental property of the quantum world. The observed outcome depends on how the system is interrogated. The electron does not reveal its wave or particle nature independently of the measurement context. By emphasizing this connection, Bohr provided a coherent conceptual framework to understand experimental results that otherwise seemed paradoxical. Observation becomes a lens that shapes reality rather than a mirror reflecting an independent world. Bohr's philosophy of measurement influenced the way quantum mechanics was formalized mathematically. In developing the theory, physicists such as Heisenberg, Schrödinger, and Dirac incorporated the understanding that observables depend on experimental context. Operators in quantum mechanics do not represent pre-existing properties of particles. They encode potential outcomes contingent on measurement. Bohr's insight about observer influence provided the philosophical justification for this mathematical structure. Without it, the abstract formalism of quantum mechanics would appear mysterious and disconnected from physical reality. Bohr bridged the gap between formalism and experiment by insisting that measurement is an inseparable component of quantum phenomena. The consequences of Bohr's perspective extend to modern quantum technologies. Quantum cryptography, quantum computing, and high-precision measurement systems all rely on the understanding that measurement influences outcomes. In quantum computing, for example, the act of reading a qubit state collapses it from a superposition of possibilities into a single outcome. Engineers and physicists design systems with this principle in mind, exploiting the observer-dependent nature of quantum states to perform computations that are impossible in classical systems. Bohr's conceptual insight, born from careful reflection on atomic spectra, underpins these advanced technologies. It demonstrates the enduring relevance of his understanding of measurement and observation beyond practical applications. Bohr's emphasis on the observer also carries profound philosophical implications. It challenges the classical notion of an objective reality entirely independent of human interaction. In the quantum framework that Bohr helped articulate, reality is not fixed. In isolation, it emerges from the interplay between system and measurement. This does not imply that nature is subjective or arbitrary, but that the structure of physical phenomena is inextricably linked to the context of observation. Human knowledge is constrained by these interactions, and the quest for understanding must take into account the limits imposed by measurement. This epistemological shift reshapes how we think about causality, determinism, and the very notion of reality. Bohr's approach to the observer problem was also marked by remarkable clarity and restraint. He did not claim that human consciousness collapses quantum states, as some later interpretations would suggest. Instead, he emphasized the physical act of measurement interaction between the system and instruments, or between different parts of the system as the key factor. The observer's influence is real, but it is not mystical. It is rooted in the unavoidable coupling between the measuring apparatus and the observed system. By keeping the explanation grounded in physical principles, Bohr avoided philosophical speculation while still making a profound conceptual leap. Throughout his career, Bohr repeatedly returned to this theme in lectures, correspondence, and debates with other physicists. His exchanges with Einstein, in particular, highlight the depth of his understanding. Einstein, who valued determinism and objective reality, challenged Bohr with thought experiments designed to expose supposed contradictions in quantum mechanics. Bohr responded with careful reasoning, demonstrating that the apparent paradoxes arose from neglecting the role of measurement and the observer. His ability to defend and clarify these ideas under intense scrutiny solidified his reputation as the leading philosophical interpreter of quantum phenomena. He had not only identified the problem but provided a framework for resolving it conceptually. Bohr's emphasis on observer influence transformed how experiments are designed, how results are interpreted, and how theories are formulated. It forced scientists to reconsider the assumptions underlying classical measurement and to develop a new experimental ethos for the quantum world. Instruments must be carefully understood, experimental setups must be rigorously defined, and outcomes must be interpreted in the context of the interaction between observer and system. Quantum mechanics is not merely a set of equations, it is a disciplined approach to knowledge that recognizes the inseparability of measurement and physical reality. The recognition that observation shapes outcomes also fosters a deeper humility in science. Classical physics, for all its predictive success, encouraged the belief that the universe could be fully known if only the right instruments were employed. Bohr's insights revealed that some limits are not technological, but structural. Measurement itself imposes constraints on what can be known. By embracing these limits, scientists gain not weakness but clarity. They learn to focus on what can be measured, predicted, and manipulated, while acknowledging the inherent boundaries of knowledge. This philosophical lesson continues to inform contemporary science, from quantum theory to complex systems research. Through the lens of Bohr's ideas, the atomic world emerges as a dynamic interplay between system and observer. Electrons occupy discrete energy levels, transitions occur in quantized steps, and the outcomes of measurements depend on the experimental setup. Classical notions of independent reality, deterministic trajectories, and neutral observation are no longer applicable. Instead, Bohr's framework introduces a new kind of logic, one in which interaction and context are central. By emphasizing the influence of observation on outcomes, he reshaped the very concept of cause and effect at the microscopic scale. This is one of the defining features of quantum thinking, and it is a direct result of Bohr's careful, insightful, and philosophically sophisticated analysis. Bohr's recognition of observer influence is not confined to esoteric laboratory phenomena. It underpins the conceptual architecture of the entire quantum revolution. The design of experiments, the formulation of theory, the interpretation of results, and even the development of quantum technologies all reflect the principle that measurement and observation shape physical outcomes. By emphasizing this point, Bohr helped create a new scientific methodology, one that accepts interaction as an intrinsic part of phenomena rather than a nuisance to be minimized. This methodology has enduring relevance, guiding how physicists approach the unknown, handle paradox, and reconcile theory with experiment. Bohr's insight into measurement continues to resonate today, not only in physics, but in philosophy, information theory, and the study of complex systems. It reminds us that knowledge is always situated, that understanding is contingent on context, and that reality is never entirely separable from the means by which it is probed. The observer is not an external spectator, but an active participant in the unfolding of physical events. This perspective challenges classical assumptions, but also enriches scientific inquiry, opening new avenues for exploration and discovery. Bohr's vision, articulated through careful study of the atom, transformed the foundations of knowledge itself. Bohr's emphasis on observer influence also shapes our understanding of probability uncertainty. In classical physics, uncertainty arises from ignorance. A sufficiently precise measurement could, in principle, reveal the exact state of a system. In the quantum framework Bohr helped create, uncertainty is intrinsic. Measurement limits are not merely technical. They reflect the fundamental structure of nature. By focusing on the interaction between observer and system, Bohr provided a conceptual basis for accepting intrinsic uncertainty as a defining feature of quantum phenomena. This insight underpins the probabilistic nature of quantum mechanics, guiding both theoretical understanding and practical experimentation. Bohr's insistence on the inseparability of measurement and outcome influenced generations of physicists and shaped the very language of quantum mechanics. Terms such as wave function collapse, eigenstates, and observables all reflect the centrality of measurement in defining reality. With Bohr's conceptual framework, these notions would lack coherence, and quantum theory would remain an abstract formalism disconnected from experimental practice. By emphasizing observer influence, Bohr integrated philosophical insight with scientific rigor, ensuring that quantum mechanics could be understood, applied, and developed in a coherent and consistent manner. The legacy of Bohr's insight extends to modern technologies that exploit quantum principles. Quantum communication, entanglement-based cryptography, and high-precision measurements all rely on the observer-dependent nature of quantum states. In designing these systems, scientists must account for how measurement interactions shape outcomes, echoing Bohr's original insight. The practical applications of this principle demonstrate its enduring importance, confirming that Bohr's philosophical and scientific contributions remain relevant and vital more than a century after they were first articulated. Bohr's emphasis on the observer also shaped debates about the interpretation of quantum mechanics. Competing frameworks: Copenhagen interpretation, many worlds interpretation, relational. Quantum mechanics all grapple with the role of observation and measurement. Even in these diverse perspectives, the centrality of interaction between observer and system can be traced back to Bohr's pioneering work. His careful reasoning provided the conceptual anchor from which subsequent discussions could depart, ensuring that debates about quantum reality remained grounded in empirical observation while exploring the philosophical consequences of measurement. As the 20th century progressed, the implications of Bohr's insight regarding the observer became increasingly apparent. Experiments that once seemed straightforward revealed the subtlety and complexity of measurement at the quantum level. Researchers found that no matter how sophisticated their instruments, the act of probing a system inevitably influenced its behavior. This principle was not a limitation of technology, but a fundamental property of nature itself. Bohr's work provided the conceptual framework necessary to understand these effects and to design experiments that could extract meaningful information despite the unavoidable influence of observation. The recognition that measurement is active rather than passive reshaped the methodology of experimental physics and forced scientists to adopt a new epistemology, one in which the observer and the observed are inseparable partners in the act of discovery. The debates that unfolded around this insight were intense and often deeply philosophical. Bohr's contemporary, Albert Einstein, famously resisted the notion that observation could influence reality. He argued that quantum mechanics must be incomplete, famously remarking that God does not play dice with the universe. Bohr's response, characterized by both clarity and philosophical depth, emphasized that quantum phenomena cannot be understood apart from the measurement context. He did not deny the existence of an objective reality but insisted that at the quantum level, reality manifests only in relation to interaction. These exchanges, which took place over decades, crystallized a central theme of modern physics: that limits of knowledge are not merely technical constraints, but fundamental features of the universe. Bohr's perspective on the observer was instrumental in framing this debate and continued to influence discussions about the interpretation of quantum mechanics to this day. In laboratory practice, Bohr's emphasis on measurement reshaped how physicists approached experiments. For instance, the development of electron diffraction techniques required a deep understanding of how the measurement apparatus interacts with the electrons being studied. Electrons exhibit both wave-like and particle-like behavior depending on the experimental setup. Bohr's framework made it clear that attempting to isolate the electrons from measurement effects entirely was not only impossible but conceptually misguided. Instead, physicists learned to design experiments with the observer in mind, accounting for the unavoidable influence of the measurement process. This approach allowed them to extract reliable data and to interpret results in a way that respected the fundamental principles Bohr had articulated. Bohr's philosophy of measurement extended beyond simple observation to the design of experimental apparatus itself. Every component of a quantum experiment, detectors, slits, screens, and sensors, could not be considered neutral. Each device interacted with the system under study, and these interactions had to be accounted for when interpreting results. This requirement represented a profound departure from classical experimental methodology, where instruments were assumed to be passive. Bohr's insight demanded a new discipline of experimental design, in which the observer's influence is treated as an integral part of the system, rather than a nuisance to be minimized. This approach has become standard practice in modern quantum research, reflecting the lasting impact of Bohr's ideas. The influence of Bohr's thinking also extended into the realm of theoretical physics. He insisted that the mathematical formalism of quantum mechanics must be interpreted in light of measurement principle. The wave function, which encodes the probabilities of different outcomes, cannot be understood as representing a particle's pre-existing properties independent of observation. Instead, it represents potential outcomes that become actualized only in the context of measurement. This conceptual framework reconciles the abstract mathematics with the observable world, ensuring that quantum mechanics remains both predictive and meaningful. Bohr's emphasis on the observer thus bridges the gap between theory and experiment, a connection that remains vital in contemporary physics. Bohr's approach to the observer problem also influenced the philosophical understanding of causality. In classical physics, causes led deterministically to effects, and the role of the observer is largely irrelevant. Quantum mechanics, however, reveals a more nuanced picture. Measurement outcomes are not strictly determined by prior conditions. They depend on the interaction between system and observer. Bohr's perspective clarifies that causality in the quantum world must be understood probabilistically and contextually. This insight has profound implications not only for physics but for broader questions about knowledge, prediction, and the nature of reality. By emphasizing the role of the observer, Bohr introduced a conceptual shift that transcends the laboratory and touches on fundamental philosophical questions. The impact of Bohr's ideas on the development of quantum theory cannot be overstated. His insistence on considering the observer in experimental and theoretical work guided the formulation of key principles, including the uncertainty principle and the Copenhagen interpretation of quantum mechanics. These principles formalize the notion that certain pairs of physical properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. The limitations imposed by measurement are intrinsic, not technical. Bohr's thinking provided the philosophical and conceptual foundation for these developments, ensuring that they were grounded in a coherent understanding of the observer's role. The principle that observation influences outcomes also has practical implications for modern quantum technologies. Quantum computing, for example, relies on the manipulation of qubits, which exist in superpositions of states. The act of measurement collapses these superpositions into definite outcomes. Designing quantum algorithms requires careful consideration of how and when measurements are performed, reflecting Bohr's insight that the observer is an active participant in the system. Similarly, quantum cryptography exploits the sensitivity of quantum states to measurement. Any attempt to intercept a quantum communication alters the system in detectable ways. These technologies demonstrate that Bohr's philosophical insights have direct, tangible applications in the modern world. Bohr's emphasis on the observer also fosters a unique form of scientific humility. By acknowledging that measurement influences outcomes, scientists recognize the limits of their knowledge and the contingent nature of observation. This perspective discourages overconfidence in deterministic predictions and encourages careful, context-sensitive inquiry. It also highlights the collaborative nature of science. Knowledge emerges not only from isolated observations, but from the interplay between experimenters, instruments, and systems. Bohr's framework thus promotes a more nuanced, sophisticated approach to understanding nature, one that continues to shape research methodologies in physics and beyond. The conceptual shift initiated by Bohr also has implications for the interpretation of quantum phenomena in complex systems. In quantum entanglement, for example, measurement of one particle instantaneously affects the state of another regardless of distance. This phenomenon challenges classical intuitions about locality and causality. Bohr's emphasis on the inseparability of observer and system provides a conceptual lens through which these phenomena can be understood. Measurement is not merely a passive record of pre-existing properties, it actively defines the state of the system within a broader experimental context. This insight allows physicists to approach entanglement and other non-classical phenomena with a coherent philosophical and methodological framework. Bohr's insights also shaped the pedagogy of quantum physics. By emphasizing the role of measurement, he trained generations of physicists to think critically about the design and interpretation of experiments. Students were taught not to take classical intuitions for granted but to consider the fundamental ways in which observation affects outcomes. This training instilled a deep respect for the complexity of quantum phenomena and a rigorous approach to scientific reasoning. Bohr's influence extended far beyond his own research. It shaped the very culture of quantum physics, fostering a generation of scientists equipped to explore the mysteries of the microscopic world with both precision and philosophical awareness. The historical significance of Bohr's emphasis on observer influence can also be seen in the evolution of quantum theory itself. As quantum mechanics developed, the concept of measurement became central to debates about interpretation, completeness, and reality. The Copenhagen interpretation, which Bohr championed, explicitly incorporates the role of the observer, asserting that quantum systems do not possess definite properties independent of measurement. This interpretation has guided research, experimental design, and theoretical development for nearly a century. Bohr's insistence on the fundamental importance of the observer ensured that these debates were grounded in a coherent and empirically informed framework. Bohr's influence extends beyond the confines of physics into philosophy and epistemology. His insights challenge classical notions of objectivity, determinism, and independent reality by demonstrating that observation is an active participant in physical phenomena. He prompted thinkers to reconsider the nature of knowledge itself. In this view, understanding is not merely a passive reflection of the world but a process shaped by interaction, context, and methodology. Bohr's emphasis on the observer provides a conceptual bridge between scientific practice and philosophical reflection, illustrating how deep scientific insights can reshape broader understandings of reality. Even in contemporary research, Bohr's perspective remains vital. Quantum technologies, from precision measurement to quantum communication and computing, rely on careful management of the interaction between observer and system. Experimental designs account for the fundamental influence of measurement, reflecting Bohr's insights into the inseparability of observation and outcome. The principles he articulated continue to guide both theoretical and practical work, demonstrating the enduring relevance of his philosophy. Bohr's emphasis on the observer has become a foundational concept in modern physics, shaping the development of the field and enabling technological innovation. Bohr's thinking also shaped the interpretation of quantum paradoxes. Thought experiments, such as Schrödinger's cat, highlight the strange consequences of observer-dependent measurement. Bohr's framework provides a way to understand these paradoxes without resorting to mystical or subjective explanation. Measurement, in his view, is a physical process that defines the state of a system in a particular experimental context. The paradox arises not from a failure of logic, but from a failure to account for the inseparability of system and observation. This perspective allows physicists to navigate the conceptual challenges of quantum mechanics with clarity and rigor, grounding abstract phenomena in a coherent philosophical framework. By emphasizing the active role of the observer, Bohr transformed the way scientists understand the nature of reality. Classical physics presented a universe that could, in principle, be fully known and described independently of observation. Bohr revealed that at the quantum level, reality is contingent upon interaction. Measurement is not merely a tool for uncovering pre-existing facts. It is a process that participates in the formation of those facts. This insight reshapes the very conception of causality, determinism, and scientific knowledge, marking a profound intellectual departure from centuries of classical thinking. The practical consequences of Bohr's insight continue to manifest in experimental physics. Techniques such as weak measurement, quantum tomography, and quantum state manipulation all rely on the careful consideration of how measurement affects outcomes. Researchers design experiments to control, exploit, or mitigate the influence of observation, reflecting the foundational principles Bohr articulated. In this sense, every modern experiment in quantum mechanics is a tribute to Bohr's insight. The observer is never separate from the observed, and the act of measurement shapes the unfolding of physical reality. Bohr's influence extends beyond the laboratory and into the broader intellectual landscape. His emphasis on observer-dependent reality challenges assumptions about objectivity, knowledge, and causality. It invites reflection on the limits of human understanding and the ways in which context shapes perception and interpretation. By integrating these philosophical considerations into the practice of science, Bohr helped cultivate a form of scientific reasoning that is both rigorous and conceptually sophisticated. His insights continue to inform debates not only in physics but in philosophy of science, epistemology, and cognitive theory. Through his emphasis on the observer, Bohr also illuminated the relational nature of quantum phenomena. Particles, waves, fields, and energy states do not exist in isolation. their properties manifest through interaction. This relational perspective provides a coherent way to understand phenomena such as entanglement, superposition, and wave function collapse. It reinforces the principle that measurement is not a neutral act, but an integral component of reality at the quantum level. Bohr's thinking allows scientists to navigate these counterintuitive phenomena with intellectual rigor, ensuring that quantum mechanics remains both predictive and conceptually coherent. In conclusion, Bohr's emphasis on the observer and the role of measurement represents one of the most profound contributions to science in the 20th century. By demonstrating that observation actively influences physical outcomes, he challenged centuries of classical assumption, reshaped experimental methodology, and provided the philosophical foundation for modern quantum mechanics. His insights continue to guide research, inform technological innovation, and inspire philosophical reflection. Bohr's vision transformed not only how scientists understand the atom, but also how they understand the act of knowing itself, establishing him as a central figure in the development of quantum thinking and one of the most influential minds in the history of science. Niels Bohr's principle of complementarity stands as one of the most profound insights in the history of science, representing a conceptual leap that redefined the way humans understand the natural world. In classical physics, phenomena were expected to be explained using mutually consistent frameworks. Light was thought to be either a particle or a wave. Matter followed clear trajectories, and observation was assumed to reveal pre-existing properties. The universe was deterministic and coherent, and contradictions were signs of failure in theory or measurement. Yet Bohr's careful study of quantum phenomena revealed that this classical expectation did not hold at the microscopic level. Nature, he argued, operates in ways that demand dual descriptions, each capturing essential truths that cannot be fully expressed through a single perspective. Complementarity, in Bohr's vision, was not merely a mathematical or philosophical tool. It was a fundamental principle describing the nature of reality itself. The roots of complementarity emerged from the study of light and matter. Early 20th century experiments had produced puzzling contradictions. The photoelectric effect explained by Einstein showed that light behaves as discrete quanta, or photons, under certain conditions. At the same time, interference and diffraction experiments demonstrated unmistakable wave-like behavior. These observations could not be reconciled using classical logic. Light appeared to be both a particle and a wave, depending on how it was measured. Bohr recognized that the solution did not lie in forcing light to conform to one category or the other. Instead, he proposed that the two seemingly contradictory behaviors were complementary. Each description reveals a facet of reality that the other cannot capture, yet together they provide a complete understanding of the phenomenon. Complementarity extends beyond light to the behavior of electrons, atoms, and all quantum systems. Electrons, for instance, exhibit particle-like impacts when detected on a screen, leaving discrete marks as if they were solid objects. Simultaneously, they display interference patterns in double-slit experiments, a property characteristic of waves. No single experiment can reveal both aspects simultaneously. Bohr argued that this duality is not a limitation of experimental design, but a fundamental feature of the microscopic world. The wave and particle descriptions are mutually exclusive in terms of measurement, yet both are necessary to fully describe quantum phenomena. Each perspective is incomplete alone, but together they offer a comprehensive understanding of nature's behavior. This principle challenged centuries of deterministic thinking. In classical physics, apparent contradictions indicated errors in measurement, calculation, or theory. Complementarity, however, asserted that apparent contradictions at the quantum level are not errors but essential truths. Reality cannot always be described in terms of a single set of properties observed independently of the measurement context. The choice of experimental setup defines which aspect of the system becomes manifest, yet neither choice can capture the full nature of the quantum object. Bohr's insight required a profound conceptual adjustment. Human understanding is constrained by the methods of observation, and phenomena reveal different truths depending on the context in which they are interrogated. Complementarity also provided a framework for interpreting wave function behavior and quantum probabilities. Classical mechanics assumes that properties like position and momentum can be known simultaneously with arbitrary precision. Quantum mechanics, in contrast, reveals inherent limitations in such simultaneous knowledge. The wave function encodes potential outcomes, but the act of measurement selects one outcome from a range of possibilities. Bohr's complementarity clarifies that different experimental arrangements reveal different properties. Measuring position precisely obscures momentum, and vice versa. These dual descriptions are not contradictory, they are complementary. Each provides partial insight, and both are required for a coherent understanding of quantum systems. The philosophical implications of complementarity extend far beyond physics. Bohr's principle suggests that knowledge itself is context-dependent. Understanding emerges through interaction between observer and system, not from the passive revelation of an independent reality. This insight transforms how scientists and philosophers approach questions of causality, determinism, and epistemology. Bohr demonstrated that human perception and measurement shape the form of reality that becomes accessible. Complementarity embodies a new way of thinking, one in which contradictions are not necessarily failures, but reflections of nature's inherent complexity. It invites a conceptual humility, reminding us that the universe cannot always be captured by a single, absolute description. In practical terms, complementarity has guided experimental design, technological innovation, and the interpretation of quantum phenomena. Researchers designing quantum optics experiments, for example, routinely consider whether to measure particle-like or wave-like properties, understanding that both cannot be accessed simultaneously in the same experimental setup. Technologies such as lasers, semiconductors, and quantum computers exploit the dual nature of light and matter, illustrating how Bohr's conceptual insights translate into practical application. Complementarity has become a cornerstone of quantum mechanics, shaping both theory and experimentation while enabling the development of transformative technologies. Complementarity also influenced the broader scientific culture. Bohr's careful articulation of this principle encouraged physicists to embrace conceptual complexity rather than resist it. In an era when deterministic, reductionist thinking dominated, Bohr provided a framework for understanding phenomena that defied classical logic. Scientists learned to accept that nature at the microscopic level operates according to rules that differ fundamentally from everyday experience. This acceptance of duality and context-dependent behavior became central to the training and mindset of generations of quantum physicists, influencing experimental methodology, theoretical reasoning, and philosophical reflection. In debates with contemporaries, complementarity served as a conceptual anchor. Bohr's exchanges with Einstein highlighted the tension between determinism and probabilistic outcomes, between classical intuition and quantum reality. Einstein sought a single, objective description of reality, while Bohr insisted on the necessity of complementary perspectives. These debates, often intense and meticulous, helped clarify the meaning and scope of quantum theory. Complementarity provided a coherent framework within which these discussions could occur, bridging the gap between experimental evidence and philosophical interpretation. Through these dialogues, Bohr's principle established itself not merely as a theoretical concept, but as a guiding philosophy for understanding the quantum world. Ultimately, complementarity reshapes the way humans think about dualities in nature. It reveals that apparent contradictions may be essential rather than accidental, that observation and context determine which properties of a system manifest, and that a full understanding requires multiple, mutually exclusive perspectives. Bohr's principle transcends the technical details of quantum mechanics, offering a profound insight into the nature of knowledge, reality, and the limits of human perception. By introducing complementarity, Bohr did not merely provide a solution to specific experimental puzzles, he transformed the intellectual landscape of physics, creating a framework that continues to inform scientific reasoning, experimental design, and philosophical reflection to this day. Niels Bohr's influence on quantum physics extended far beyond his own groundbreaking research. It is perhaps equally embodied in his role as a mentor and leader. At the Copenhagen Institute for Theoretical Physics, he cultivated an environment that became the intellectual epicenter of quantum mechanics, attracting the brightest minds from around the world. Bohr understood that scientific progress is not only about individual genius but also about creating a space where ideas can be challenged, refined, and expanded collaboratively. His mentorship combined rigorous scientific scrutiny with a deep respect for intellectual creativity, producing generations of physicists whose work would define the future of the field. The impact of this guidance is difficult to overstate, as it shaped the very way quantum theory developed and ensured that Bohr's vision extended far beyond his own lifetime. The culture Bohr fostered was unusual for its time. Unlike the rigid hierarchies typical in many academic institutions, the Copenhagen Institute encouraged informal discussion, open debate, and intellectual exploration. Students and visiting scientists alike were invited to engage directly with Bohr, posing questions, presenting ideas, and challenging assumptions. Late-night conversations in Bohr's office, often stretching into the early hours, became legendary for their depth and intensity. Bohr had a remarkable ability to listen patiently, discern the essence of an argument, and guide his colleagues toward clarity without dictating conclusions. This approach nurtured independence of thought, helping young physicists develop confidence in their own reasoning while remaining grounded in the rigor of empirical science. Among the scientists influenced by Bohr were some of the most iconic figures of 20th century physics. Werner Heisenberg, who formulated matrix mechanics and the uncertainty principle, benefited directly from Bohr's guidance. Bohr's insistence on considering both experimental context and theoretical consistency helped Heisenberg navigate the conceptual challenges of quantum mechanics. Similarly, Wolfgang Pauli, known for the Pauli exclusion principle, found in Bohr a mentor capable of blending philosophical insight with technical mastery, encouraging rigorous thought while fostering creative exploration. Even Paul Dirac and others who later became giants in the field were shaped by the intellectual atmosphere Bohr created, which emphasized dialogue, reflection, and the careful integration of theory and experiment. Bohr's mentorship was distinctive not only for its intellectual rigor but also for its moral and ethical dimension. He emphasized that scientific discovery carries responsibility. Knowledge, especially in a field as revolutionary as quantum mechanics, must be pursued with integrity and humility. This approach left a lasting impression on his students, instilling a culture of thoughtful, conscientious research. Bohr believed that understanding nature was not merely a technical achievement, but also a philosophical and ethical endeavor. His mentorship, therefore, went beyond guiding experiments or calculation. It shaped the character and judgment of future leaders in science. The Copenhagen Institute itself became a crucible for collaborative innovation. Bohr's leadership ensured that it was not merely a place to learn existing theories but a forum to invent new ones. Young physicists were encouraged to grapple with paradoxes, explore conceptual contradictions, and confront the limits of classical thinking. Bohr's guidance was particularly influential when they encountered the counterintuitive aspect of quantum theory, such as wave-particle duality, uncertainty, and complementarity. Rather than imposing rigid solutions, he cultivated the ability to tolerate ambiguity, to reason through complexity, and to synthesize multiple perspectives. This intellectual training proved essential as quantum mechanics rapidly evolved, enabling his protégés to contribute foundational breakthroughs with confidence and originality. Bohr's mentorship also extended internationally, drawing young scientists from across Europe and beyond to Copenhagen. The institute became a hub of cross-cultural scientific exchange, where ideas flowed freely despite linguistic, national, and philosophical differences. Bohr's diplomacy and openness fostered collaboration, even in politically turbulent times, reinforcing the principle that scientific truth transcends borders. By mentoring diverse talent and encouraging open exchange, Bohr ensured that the development of quantum theory was a collective enterprise, enriched by multiple perspectives and approaches. His leadership thus shaped not only individual careers, but also the global trajectory of physics. In addition to intellectual guidance, Bohr played a critical role in shaping experimental and theoretical priorities. He had an uncanny ability to identify which questions were most pressing and which conceptual frameworks held the greatest potential for insight. Young scientists learned to approach their work with a sense of purpose, guided by Bohr's strategic vision of the field. He was not a domineering figure but a facilitator, helping others recognize the implication of their work and its connection to the broader landscape of quantum theory. This combination of mentorship, vision, and philosophical grounding created an enduring legacy that extended far beyond the immediate results of individual experiments. Bohr's influence on the next generation also included fostering the philosophical understanding of quantum mechanics. He encouraged students to reflect deeply on the implications of their work, to consider the limits of knowledge, and to confront the counterintuitive nature of the quantum world. Through dialogue and debate, young physicists learn not only to calculate and predict but to interpret and conceptualize. Bohr's mentorship, therefore, prepared scientists to think critically about the meaning and significance of their discovery, a quality that has defined the practice of theoretical physics to this day. The legacy of Bohr's leadership is evident in the enduring contributions of his students and collaborators. Many of them went on to become leaders of major research institutions, guiding new generations of physicists and continuing to explore the frontiers of quantum theory. The culture of rigorous inquiry, collaborative debate, and philosophical reflection that Bohr established became embedded in the very fabric of modern physics. His approach demonstrated that scientific progress depends not only on individual brilliance, but also on mentorship, community, and the cultivation of an intellectual ecosystem that nurtures creativity and critical thought. Bohr's mentorship was characterized by patience, empathy, and a subtle form of intellectual encouragement. He recognized that grappling with quantum paradoxes could be intellectually disorienting and emotionally taxing. Rather than dismissing confusion or demanding immediate solutions, he provided a supportive environment in which questions could be explored safely and rigorously. This approach helped scientists navigate the uncertainties and complexity of their work, fostering resilience, curiosity, and independent thinking. Bohr's students emerged not only as skilled researchers, but as reflective, thoughtful practitioners capable of pushing the boundaries of knowledge while remaining grounded in rigorous methodology. Even beyond his lifetime, Bohr's influence continues to shape physics. The values he instilled, collaboration, conceptual clarity, intellectual humility, and philosophical awareness, remain integral to the practice of science. The Copenhagen Institute, though now part of a broader historical narrative, serves as a symbol of how leadership, mentorship, and intellectual culture can accelerate scientific progress. Bohr's ability to nurture talent, inspire creativity, and guide conceptual development ensured that his revolutionary insights into quantum mechanics were not isolated achievements, but the foundation for an entire scientific tradition. His mentorship exemplifies the human dimension of science, showing that ideas flourish not only through individual genius, but through the careful cultivation of minds, dialogue, and community. Through his guidance, Bohr demonstrated that the advancement of knowledge is inseparable from the growth of those who pursue it. His mentorship created a lineage of physicists equipped not only with technical skill but with the intellectual agility to navigate the conceptual challenges of the quantum world. By fostering creativity, debate, and rigorous reasoning, Bohr ensured that his vision of quantum mechanics would continue to evolve long after he was gone. This combination of personal mentorship and intellectual leadership is a defining aspect of his legacy, underscoring the importance of human relationships and community in the unfolding of scientific discovery. Ultimately, Bohr's mentorship and leadership exemplify the synthesis of insight, vision, and human empathy. He recognized that nurturing the next generation of scientists was not merely a responsibility, but a central means of advancing knowledge itself. By creating an environment in which intellectual curiosity, rigorous analysis, and philosophical reflection could thrive, together, Bohr ensured that quantum physics developed as a coherent, dynamic, and profoundly transformative field. His influence on students, collaborators, and the broader scientific community underscores the enduring power of mentorship in shaping both individual minds and the trajectory of scientific history. Bohr's guidance transformed potential into achievement, curiosity into discovery, and uncertainty into insight, securing his place as a central figure in the development of modern science. Niels Bohr's intellectual legacy is inseparable from his famous debates with Albert Einstein, discussions that spanned decades and delved into the deepest philosophical questions about the nature of reality. These debates were not mere academic exercises, They were central to the development of quantum mechanics and shaped the conceptual foundations of the field. Einstein, the champion of determinism and classical objectivity, challenged the emerging quantum theory at every turn, arguing that it could not provide a complete description of physical reality. Bohr, in contrast, insisted that quantum mechanics, with all its apparent paradoxes, offered the most accurate and coherent description of nature possible. Their exchanges illuminated the profound conceptual challenges of the atomic world and clarified the philosophical stakes involved in understanding quantum phenomena. The essence of the Bohr-Einstein debates revolved around the interpretation of quantum mechanics. Einstein was troubled by the probabilistic nature of the theory of the implications of wave function collapse. He believed that there must be hidden variables, underlying deterministic processes that quantum mechanics had yet to uncover. Bohr, however, argued that the theory was complete in its probabilistic form, and that the apparent uncertainties reflected fundamental properties of nature, rather than limitations of knowledge. Central to Bohr's position was the idea that measurement and observation are inseparable from the phenomena being studied. Quantum systems do not possess definite properties independent of the measurement context. Instead, properties emerge in relation to observation. This principle of observer dependence was a point of contention between the two great physicists, highlighting the philosophical depth of their debates. One of the most famous thought experiments illustrating this tension was the Einstein-Podolsky-Rosen EPR paradox. In 1935, Einstein and his colleagues proposed a scenario in which two particles become entangled, meaning the measurement of one instantaneously affects the state of the other, regardless of distance. Einstein viewed this as evidence that quantum mechanics was incomplete, famously calling it spooky action at a distance. Bohr responded with a meticulous analysis, emphasizing that the paradox arose from a misunderstanding of the role of measurement and the relational nature of quantum properties. He demonstrated that entanglement does not violate causality or relativity, but instead reflects the fundamental principle that the properties of quantum systems are context-dependent. Bohr's response not only addressed the specific challenge posed by the EPR paradox, but also clarified the philosophical underpinning of the theory, reinforcing the idea that reality at the quantum level cannot be separated from experimental context. The debates were characterized by their rigor, precision, and mutual respect, even when the positions of the two physicists seemed irreconcilable. Einstein presented carefully crafted thought experiments designed to expose supposed contradictions in quantum mechanics, while Bohr responded with equally precise reasoning, often highlighting subtle conceptual misunderstandings. These exchanges required extraordinary clarity of thought, a deep understanding of both experimental practice and theoretical principles, and a willingness to grapple with counterintuitive ideas. The intensity of their dialogue pushed both men to refine their arguments, consider alternative perspectives, and articulate the foundational principles of quantum mechanics with unprecedented sophistication. Bohr's approach to these debates was grounded in both scientific pragmatism and philosophical reflection. He recognized that quantum mechanics, unlike classical physics, challenges intuitive notions of reality, causality, and determinism. Rather than attempting to force nature into pre-existing conceptual frameworks, Bohr sought to develop principles that accurately reflected experimental evidence. His insistence on complementarity, the inseparability of measurement and outcome, and the probabilistic interpretation of quantum phenomena all emerged from this philosophical stance. The debates with Einstein served as a testing ground for these ideas, providing the intellectual pressure necessary to refine and articulate them clearly. The Bohr-Einstein debates also had profound educational and cultural impact. They exemplified how scientific discourse can address both technical and philosophical questions with rigor and civility. Students, colleagues, and subsequent generations of physicists were able to witness two of the greatest minds confronting the most fundamental questions about reality. These debates became models for how to combine careful theoretical analysis with deep conceptual reflection, demonstrating that scientific progress often requires confronting not only experimental data, but also the philosophical assumptions underlying interpretation. Beyond the historical contest, Bohr's engagement with Einstein shaped the methodology and interpretive strategies of quantum mechanics. By defending the completeness of the theory, Bohr reinforced the importance of understanding measurement, observer dependence, and complementarity as central principles. Experimentalists learned to design investigations that acknowledged these conceptual foundations, ensuring that quantum theory remained coherent with observed phenomena. The debates highlighted that theory and experiment are not separate domains but interdependent aspects of scientific understanding. Bohr's insistence on integrating philosophical insight with empirical rigor influenced not only his contemporaries but also the structure of quantum research for decades to come. Bohr's philosophical sophistication allowed him to navigate the counterintuitive consequences of quantum theory while maintaining scientific clarity. He understood that classical intuitions about determinism, locality, and objectivity do not fully apply to the quantum world. The debates with Einstein made these conceptual shifts explicit, forcing the scientific community to confront the radical implications of quantum mechanics. Bohr's articulation of principles such as complementarity and observer dependence emerged directly from this dialectic, demonstrate that conceptual clarity and philosophical reflection are as essential to scientific progress as experimentation and calculation. The enduring significance of the Bohr-Einstein debates lies in their demonstration that physics is not only about equations and measurements, but also about interpretation and understanding. Bohr's ability to defend quantum mechanics against Einstein's objections provided a philosophical framework that guided the development of the Copenhagen interpretation, which remains the most widely taught and applied framework in quantum physics. By articulating why apparent paradoxes do not indicate incompleteness, but rather reflect fundamental features of nature, Bohr helped stabilize the conceptual foundations of the theory and provided future physicists with the tools to advance research confidently. Moreover, these debates influenced the international scientific community by emphasizing the importance of dialogue, skepticism, and critical reflection. Bohr's engagement with Einstein showed that scientific disagreements, when approached with rigor and respect, can clarify principles, stimulate innovation, and advance collective understanding. The debates also highlighted the interplay between theory and experiment, demonstrating that philosophical insight can inform experimental design and interpretation. Bohr's skillful navigation of these challenges exemplified the integration of scientific methodology and philosophical reasoning, a hallmark of his intellectual legacy. Bohr's debates with Einstein also resonate beyond physics, influencing broader philosophical discussions about knowledge, reality, and certainty. They illustrate that scientific theories do not merely describe phenomena, they provide framework for interpreting observations, resolving contradictions, and understanding the limits of knowledge. Bohr's insistence that quantum mechanics is complete, despite its probabilistic nature, challenges traditional notions of determinism and objectivity while providing a coherent basis for understanding reality at the smallest scales. These philosophical insights continue to inform both scientific and philosophical inquiry, demonstrating the lasting impact of Bohr's intellectual engagement. In essence, Bohr's debates with Einstein were a crucible in which the conceptual foundations of quantum mechanics were forged. Through careful reasoning, philosophical sophistication, and rigorous engagement with experimental evidence, Bohr articulated principles that remain central to the field: complementarity, observer dependence, and the probabilistic nature of quantum phenomena. The debates clarified the meaning of quantum theory, resolved apparent paradoxes, and shaped the intellectual culture of physics. By confronting Einstein's challenges directly, Bohr strengthened the theoretical framework of quantum mechanics and ensured that its philosophical and scientific foundations were both coherent and enduring. The debates also exemplify Bohr's broader intellectual style, a combination of patience, subtlety, and philosophical depth. He engaged opponents with respect, listened carefully, and guided them through the conceptual landscape of quantum theory without resorting to rhetoric or dismissal. This approach allowed him to defend quantum mechanics convincingly, while also clarifying its broader philosophical implications. Bohr's ability to balance scientific rigor with philosophical insight ensured that the field could advance in both conceptual clarity and empirical sophistication, setting a standard for scientific discourse that continues to inspire physicists today. Ultimately, Bohr's engagement with Einstein shaped the way the world understands quantum mechanics. By defending the theory against rigorous critique, Bohr provided a coherent philosophical framework that integrates measurement, probability, and complementarity. His responses clarified that quantum mechanics does not merely describe the behavior of particles but also redefine the relationship between observer and system, between theory and experiment, and between knowledge and reality. These debates are a testament to Bohr's intellectual leadership, demonstrating that the development of science depends not only on discovery but also on careful reasoning, philosophical insight, and the courage to confront profound, conceptual challenges. Niels Bohr's influence on modern science extends far beyond the theoretical development of quantum mechanics. It permeates contemporary research, technology, and our fundamental understanding of the physical world. His insights into the atomic structure, complementarity, and the role of observation established conceptual frameworks that continue to guide both experimentation and innovation. The principles Bohr articulated have proven essential not only in interpreting the behavior of particles at the quantum scale but also in developing practical applications that have transformed technology, industry, and society. From quantum computing to semiconductors, Bohr's intellectual contributions form the backbone of many modern advances, demonstrating the enduring power of foundational scientific insight. The influence of Bohr's work is particularly evident in the field of quantum computing. Quantum bits, or qubits, exploit principles such as superposition and entanglement, phenomena that were central to Bohr's theoretical exploration. The understanding that quantum systems can exist in multiple states simultaneously and that measurement collapses these states into definite outcomes is directly linked to Bohr's ideas about observer dependence and complementarity. Designing quantum algorithms requires careful consideration of how and when measurements are made, reflecting Bohr's insight that observation is not passive but an active component in the unfolding of quantum phenomena. Without his foundational principles, the conceptual basis for this revolutionary technology would be incomplete, and its development would be far more uncertain. Semiconductors and modern electronics also owe a conceptual debt to Bohr. The understanding of electron behavior within atoms, energy levels, and quantum transition underpins the design of transistors, diodes, and integrated circuits. Bohr's model of the atom, though later refined, introduced the idea that electrons occupy discrete energy states, a concept essential to predicting and controlling the flow of electricity in solid-state devices. These discoveries laid the groundwork for the digital revolution, enabling technology that formed the foundation of modern communication, computation, and information storage. In this sense, Bohr's theoretical work directly connects abstract physics with tangible technological outcomes, illustrating the practical relevance of deep conceptual understanding. Bohr's legacy is also evident in the realm of quantum optics and photonics. Lasers, which rely on the precise control of photon emission and energy transitions, are grounded in principles first explored in Bohr's studies of atomic structure and radiation. His insights into quantized energy levels, emission, and absorption processes provide the theoretical framework necessary to engineer light-based technologies with unprecedented precision. These technologies impact a wide range of fields, from medicine and telecommunications to manufacturing and fundamental research, demonstrating the broad societal implications of Bohr's contributions. The ability to manipulate quantum systems with such control reflects the enduring relevance of the ideas he introduced nearly a century ago. In experimental physics, Bohr's emphasis on the role of measurement continues to guide methodology. Precision experiments, whether in particle accelerators, quantum simulators, or atomic clock, are designed with careful attention to the observer effect and the limitations it imposes. Bohr's insights into the inseparability of system and measurement have become standard consideration, ensuring that experimental outcomes are interpreted accurately and meaningfully. Researchers planning experiments must account for how instruments interact with quantum systems, demonstrating that Bohr's conceptual contributions are not merely historical artifacts, but active principles shaping the practice of science in the modern era. Bohr's philosophical insights have also influenced interdisciplinary research, shaping how scientists approach complex systems beyond physics. Concepts such as contextuality, observer dependence, and complementarity inspire thinking in fields as diverse as chemistry, biology, and even cognitive science. Understanding systems in which outcomes are influenced by interaction and context reflects the enduring relevance of Bohr ideas, by demonstrating that observation and interaction fundamentally shape the properties of systems. Bohr's principles encourage researchers to adopt holistic, integrative approaches, revealing connections across disciplines that might otherwise remain obscure. The educational legacy of Bohr is equally significant. His approach to mentoring, fostering debate, and integrating conceptual reflection with rigorous experimentation has become a model for training new generations of scientists. Students and researchers exposed to Bohr's methods learn not only the technical skills necessary for research but also the philosophical perspective required to interpret results in a broader context. This approach ensures that scientific inquiry remains both rigorous and reflective, preserving the intellectual culture that Bohr cultivated while encouraging innovation and critical thinking. His impact thus extends beyond specific discoveries to the very way science is taught, learned, and practiced. Bohr's influence is also embedded in the ongoing debates surrounding the interpretation of quantum mechanics. His articulation of the Copenhagen interpretation, emphasizing probabilistic outcomes, complementarity, and the centrality of measurement, remains a reference point for both theoretical development and philosophical inquiry. Contemporary physicists, philosophers, and educators continue to grapple with the questions Bohr highlighted: the nature of reality at the quantum scale, the role of observation, and the limits of human knowledge. The fact that these debates remain vibrant nearly a century after Bohr first proposed his ideas attests to the depth and enduring significance of his contributions. Beyond theoretical and technological implications, Bohr's legacy embodies a vision of science as an integrative, reflective, and collaborative endeavor. His insistence on blending philosophical insight with empirical rigor, fostering international collaboration, and mentoring successive generations of scientists created an intellectual ecosystem that continues to thrive. Institutions, research centers, and collaborative networks worldwide reflect the principles Bohr championed: open inquiry, respect for diverse perspectives, and a commitment to both conceptual clarity and practical application. These values have become hallmarks of modern scientific practice, illustrating how Bohr's influence extends beyond specific discoveries to shape the culture and methodology of science itself. Modern applications of Bohr's ideas continue to expand with technological and scientific innovation. Quantum communication, which relies on entanglement and the sensitivity of quantum state to observation, embodies his insights into measurement and observer influence. Atomic clocks, essential for global navigation and timing systems, depend on precise manipulation of quantum states predicted by principles rooted in Bohr's atomic theory. Even the exploration of quantum biology and the study of coherency in living systems draw upon the conceptual foundations he established. Across disciplines and applications, the patterns of thought Bohr introduced continue to guide inquiry, problem-solving, and the translation of abstract theory into practical capability. Ultimately, Bohr's legacy is one of both discovery and inspiration. He provided a framework for understanding the quantum world, a method for exploring it, and a vision for how knowledge should be pursued. His work transformed the scientific understanding of matter and energy, guided the development of revolutionary technologies, and reshaped philosophical approaches to knowledge and observation. The principles he articulated continue to illuminate the frontiers of research, offering a coherent foundation upon which new generations of scientists build. Bohr's enduring influence is a testament to the power of insight, reflection, and intellectual leadership, securing his place not only as a pioneer of quantum mechanics, but as a guiding figure for modern science as a whole. Bohr's life and work illustrate that the pursuit of knowledge is a continuous dialogue between theory and experiment, imagination and observation. His insights remain embedded in laboratories, classrooms, and technological innovations worldwide, shaping the way humanity engages with the microscopic world and pushing the boundaries of what is possible. The legacy he left behind is not confined to textbooks or historical accounts. It lives in the technologies, methodologies, and conceptual frameworks that define contemporary science. Through his work, Bohr ensured that the exploration of the quantum universe would remain both intellectually rigorous and profoundly transformative, bridging the gap between human curiosity and the underlying structure of reality itself.